I'm gonna beautifully frame today why we need to connect resistors in series. I'll also show you what will happen to the magnitude of current and potential difference in the total circuit and in individual resistors connected in series. Alright, I'll also show you how to calculate the total resistance for resistors connected in series. Alright, and finally we'll see how to solve numericals based on this. Let me come again. Let me make it that simple for today's class. We'll take three resistors, R1, R2 and R3. Alright, these three resistors we're gonna join in series. Alright, across a circuit. So once we join these resistors in series, we'll see what will happen to the magnitude of current and potential difference. To do so, we'll apply Ohm's law. Okay. Next, we will see how to derive the formula for resistors connected in series, and finally we'll do some numerical. I hope you got me a very clear picture what I will try to frame in today's class. Dear viewer, I welcome you in classes with brilliant group of institution Doha, Qatar. Sticking to the point, what is a series connection is? Alright, so when resistors are joined, one after another, alright, or end to end. Alright, such a connection is said to be in series. Everybody, this is a series connection for you where I did join resistors end to end or one after another. Okay, let me write a script for you that when resistors say R1, okay, R2 and R3. So here I took R1, alright, R2 and R3. So how I connected end to end, right? So when resistors say R1, R2 and R3 connected end to end. So this could be also one after another. Alright, then the combination is said to be in series connection. So I got a very clear picture now that what is a series connection is when resistors are joined end to end or one after another. So what is my next? Next I'm going to show you what is the total resistance formula. You will tell me that's the total resistance in series. RS stands for total resistance in series, going to be sum of individual resistors R1 plus R2 plus R3. So this is the formula I was talking in the beginning, that I will derive this formula which comes for 3 marks in your exam. Alright. So to have a look here. Say suppose R1 value I took 5 ohm, R2 value I took 3 ohm and R3 value I took 2 ohm. And I ask you what is the total resistance. Look at the formula. All you need to do is you need to add the individual resistors, right? So when you add, you get 5, 3 and 2. What is the total resistance? You will tell me, sir, it is 10 ohm. Alright. So this is it. This formula we're going to derive, and you need to know 2 specific points about resistors joined in series, which I am writing in a script first of all, and then I will show you in the diagram. So it is like that. The total current in the circuit remains same in individual resistors connected in series. All right, the next one, total PD in the circuit does not remains same in individual resistors. So this is it. These 2 statements, let me see what I wrote for you. So the first statement is, guys, if the total current, let me consider the total current to be 5 ampere, all right? So the total current in the ammeter right now, the reading is 5 ampere, correct? Flowing from positive terminal to negative terminal, right? Now this total current gonna remain same here, okay, in this resistor, 5 ampere. What about this resistor? It gonna remain same. What about this resistor? It gonna remain same, all right? So what I'm telling you clearly is total current in the circuit remains same in individual resistors, all right? So what is the way of seeing it? All you need to do is that you will take this ammeter, okay, join it over this point, and this point. Simple mathematics to get this answer, that the total current remains same in individual resistors, all right? Total current of the circuit. What is the other way? The other way is numerical by applying Ohm's law, which we will see it today, all right? This statement I'm gonna prove it today. So next one, total potential difference in the circuit does not remain same in individual resistor. What I mean is, if I take the total potential difference is suppose 15 volt, okay? If you fix the voltmeter over here, okay, across R1, parallel to R1, what you will see, this 15 volt does not remain same. Do the same thing for here and here, connecting this one here and here, all right? So you will see the potential difference does not remain same. So this is it, all right? What is a series connection? You're gonna tell me that when resistors are joined end to end or one after another across a circuit. Perfect. What is the next one? The next one is the total resistance. Rs is equals with R1 plus R2 plus R3 is the formula. So as many as you can connect. All right. So what is two specific point about series connection? The first point is total current in the circuit gonna remain same in individual resistors. All right. And the total potential difference in the circuit does not remain same in individual resistors. Beautiful. So this is what I am trying to explain, that while we connect resistors in series, what gonna happen to the current? What gonna happen to the potential difference? How to calculate the total resistance? There you go, you have a formula right now, okay? And few numericals. Let me start the first numerical, number 1. Now, to get this answer, you need to know what was Ohm's law formula, right? Formulation of Ohm's law, what I mean. So formulation of Ohm's law was V is equals with IR, right? Potential difference equals with current into resistance. All right. So can I make this formula like that? So very simple thing. Let me see it. So I can make it I will be equals with V divided by R, right? Or I can make it R is equals with V divided by I, right guys? Correct. So this is the derived formula, whereas this is the root formula. Done. So I'm showing you this formula because we need a use of it in solving this numerical. Okay, the first numerical tells that an electric lamp whose resistance is 20 ohm. So instead of lamp, I will take a bulb like that. Okay, what is its resistance value? Let it be R1 is given how much? 20 ohm in the first part of the question, 20 ohm. Second part, a conductor of resistance 4 ohm. Now that conductor, let me take a resistor like that. I joined a resistor here. All right. So how much is that? R2 will be equals with how much? 4 ohm. Perfect. Now 6 volt battery. Now the battery value is given 6 volt. All right. Now they're asking us to get the total resistance in the circuit. Total resistance in the circuit. What was your formula? Total resistance in the circuit for 2 appliances, you're gonna make R1 plus R2. All right. Which we did for the 3 here. Total resistance is equals with R1 plus R2 plus R3. All right. Right now we are doing R1 plus R2 for 2 appliances connected. All right. So what's the value for R1? You're gonna tell me, sir, it was 20. So I'll fix it like that. 20 ohm plus R2 is how much? 4 ohm. So I'll make it 4 ohm like that. What's your answer? You're gonna tell me, sir, it is 24 ohm. Perfect. All right, easy. So what's the next one? Next one, total resistance of the circuit. We did, sorry, the total current through the circuit. So I want to find out total current through the circuit. So this was your A part. So B part is telling total current. What's the formula? I will be equals with V divided by R. Okay, I will be equals with V divided by R. I will be equals with V divided by R. All right. So since I am finding out the total current in the circuit, I need the total potential difference. How much is that? 6 volt. I need the total resistance. How much is that? 24. All right. Then you're going to cancel it. Okay. 6, 1, 6. How many times? 4 times. Divide it. Let me do it. 0.0, right? So you get 2 times 8, you have 2, 0 and 5. What's your answer? Your answer is 0.25 ampere. So what is the ammeter reading? You will tell me, sir, 0.25. That meaning current flow right now in the total circuit is how much? Equals with 0.25 ampere. Alright. Now I'm gonna ask you, will this total current remain same here and here? See over here. The total current remains same in individual resistors, right? Yes or no? Yes or no? So you're gonna tell me that, sir, yes, the total current flowing here in this lamp will be 0.25. Okay. In this resistor, this is gonna be how much? 0.25 ampere as well. Now once I know that what is the current value I have here, what is the current value I have here, can I find out the potential difference? That's what the next question is. For point C, the potential difference across electric lamp for point C. Okay, so PD across lamp. All right, so what's the formula? You will tell me, sir, V is equals with IR, right? V is equals with IR. What's your formula? V is equals with IR is your formula. V is equals with IR is my formula. So what is the total current for the lamp? You have 0.25. What is the total resistance you have? 20. All right. So any number you multiply with 5 will be half of this number, right? I mean, any number you multiply with 0.5 will be half of this number. Right now you are multiplying with 0.25 will be half of half number. Hack in mathematics, okay? Half of 20 will be 10. Half of 10 will be 5. Or multiply it in a regular way, you will get 5 volt or half of half, right? So that's how you get calculated and you got your value as 5 volt. Perfect. So what is the next part? Next one is total current in the conductor. In this conductor, I mean total potential difference, sorry, in the conductor. So what's the formula? You will tell me, sir. Here for the conductor, now PD for conductor, PD for conductor. So PD for conductor, V is equals with IR, right? So what is the current value? 0.25 into what is the resistance? You have 4. So what I told you, any number you multiply with 0.5, half of half number. So half of 4 is 2 and half of 2 is 1. That's what I mean. All right, let it be V1 and let it be V2. V1 for lamp, V2 for conductor. See one point over here. If you don't know the concept that the current is remaining same in individual resistor, I mean the total current is remaining same in individual resistor, could you do this formula? I mean, would you do this numerical? Could you solve this part? No. All right, you need to know a concept that the current is remaining same. Then only you can take this current and put it over here to solve the asked part. All right, so I guess you are getting me very clear how to do with it. Okay, now let me have a look in the second part of the statement. Which statement? This statement. Did I told you the potential difference in the circuit does not remain same in individual resistors, right? So let me have a look. What is the total potential difference you have? You're going to tell me, sir, 6 volt is given. All right, so how much you got here? For the lamp you got 5 volt. Yes. How much you have got for conductor? You have got 1 volt. Tell me, sir, is potential difference remaining same? No, it is not remaining same. Is current is remaining same? The total current is remaining same in the resistors. You're going to tell me, yes, sir. So I guess you got a very clear picture of this statement now numerically, which you do it by using ammeter and voltmeter, that the total current in the circuit remains same in individual resistor and total PD in the circuit does not remain same in individual resistor. All right, now let me have a look how to derive this. All right, so let me join the 3 resistor like that once again. Let it be R1, okay, let it be R2, all right, and let it be R3. Okay, so let me tell you that let V be the total PD across the circuit. So I consider V be the total potential difference across the circuit. So if V is the total potential difference of the circuit, will this total potential difference remain same in V R1, R2 and R3? You will tell me no, sir, right? So let me take V1, let me take V2, let me take V3. So how you will see it practically by connecting a voltmeter like that. Okay, in this point you connect a voltmeter. All right, same you can connect the voltmeter in this point, same you can connect the voltmeter on this point. So when you do this, you will figure out that the potential differences does not remaining same, or just now we have seen it by doing one numerical. So let V be the total potential difference in the circuit. All right, let V be the total potential difference in the circuit, and V1, V2 and V3. So V1, V2 and V3 be the PD across, all right, resistors where R1, R2 and R3. All right, so what is next? Next, here one specific point you need to see, the total potential difference was B, right, will be equals with sum of individual potential difference. What I am telling you, the total potential difference will be equal to the sum of individual potential differences. This I will take it as equation number 1. So let me have a look. See, what is the total potential difference in the circuit? You will tell me 6 volt. All right. What is the individual? 5 volt and 1 volt. So can I make it like that? Total potential difference 6 volt is equals with sum of individual potential difference 5 volt and 1 volt. Getting it? So what I have seen in the previous case, I can write it V is equals with V1 plus V2. Yes, total potential difference V is equals with V1 plus V2. Getting it? So this is what I did over here. See, numericals makes us the thing very easy in life, but we are running away of numerical, right? So V is equals with V1 plus V2 plus V3. The total potential difference will be V1 plus V2 plus V3. All right. So what is next? Next, I'm gonna pass a total current I. Okay. Then I write over here, let I be the net current. Net means the total current in the circuit. Okay, then current in R1 will be equals with I. R2 will be equals with I, R3 will be also equals with I. If I take net current as I, over here current will be I, over here current will be I, over here also current will be I. Current is not changing, right? So current remains same in individual resistors. So this is it. Once you know this, that the potential difference is not remaining, see what you are doing it, the same thing, right? Total potential difference does not remain same. Okay, total current is remaining same, right? The same thing we are doing, which we wrote in a statement like that. Okay, and we got one equation over here. Now we need to apply Ohm's law 4 times. Okay, we need to apply Ohm's law how many times? 4 times. What was Ohm's law? You will tell me, sir, V is equals with IR, right? So we'll apply how many times? 4 times. So how? See, first of all, we will apply the Ohm's law in total circuit. So applying, all right, Ohm's law in total circuit. So I applied Ohm's law in total circuit. So what was Ohm's law? You're gonna tell me, sir, V is equals with IR. Now total potential difference is V, total current is I. What was the total resistance connected in series? RS, right? So this is your equation number 2. All right. Then applying Ohm's law. Okay, individually in R1, R2 and R3. There you go. First you applied Ohm's law in the total circuit, all right, then in R1, R2 and R3. So how many times? Total 4 times. So first in total circuit, individually in R1, R2 and R3, total 4 times you need to apply the Ohm's law. All right, so let me go. So when you apply Ohm's law over here, what is your Ohm's law comes across? So you will tell me, sir, V1, just see it and relate it. V1 is equals with IR1, right? So V1 is equals with IR1. Over here, V2 is equals with IR2, right? So V2 is equals with IR2, all right? Over here, V3 is equals with IR3. So V3 is equals with IR3. So let me frame it again. Let me take it equation number 3. All right, let me take it equation number 4. And here equation number 5. This is it. You got the answer. This is it. You got the answer. What you did? You did this what you learned. Okay. What you learned? You took a potential difference V. All right. Which won't gonna remain same over here. So you took V1, V2 and V3. All right, you took total current as I, which won't gonna which will remain same, I, and I. All right, so what you have did here once again, you did here what you have learned. All right, the total potential difference does not remain same in individual resistors. So you took V1, V2 and V3. Okay, the total current remains same in individual resistors. So you took total current as I, you took I, and I. All right. Once you did this, you applied Ohm's law 4 times. All right. What is that? In the total circuit, you apply Ohm's law, you got this. Okay. Individually in R1, R2 and R3, R1, R2 and R3, you applied Ohm's law and you got this. Okay. Next, I will ask you to put equation 2, equation 3, equation 4 and equation 5. All right. Where? In equation 1. So have a look. Equation 1, equation 2, 3, 4 and 5 I am putting over here. Okay. So what was equation number 1? Equation number 1 was V is equals with V1 plus V2 plus V3. Right. So you can add here putting, right, putting equation 2, 3, 4 and 5, where in equation 1. All right, so this was your equation 1. So let me have a look. So replacing V, I can write IRS. See, replacing V, I will write IRS. Replacing V1, I will write IR1. Replacing V2, I will write IR2. Replacing V3, I will write IR3. Once again, replacing V is equals with IRS. So I will write IRS. Replacing V1, I will write IR1. Replacing V2, I will write IR2. Replacing V3, I will write IR3. So this is it. So I will write IRS. Replacing V, IRS. Replacing V1, IR1. Replacing V2, IR2. Replacing V3, IR3. All right. After that, you will take I common. So RS will be equals with I common, right? R1 plus R2 plus R3. All right. So I and I will get cancelled, and there you go. This is how you got your formula. RS is equals with R1 plus R2 plus R3. All right. So total resistance is equals with sum of individual resistors. Let me reframe it again how we did this. All right. So what you did was what you have learned. All right. You have taken the total potential differences V, and you know total potential difference does not remain same in individual resistors, right? In R1, R2 and R3. So since it is not remaining same, you have taken V1, V2 and V3. Right. Next point was if you've taken total current I, which will remain same in individual resistor R1, R2 and R3. Since it is remaining same, so you have to taken I and I everywhere. All right. This is what you have wrote. And to get equation number 1, total potential difference will be sum of individual potential differences. All right. Then you applied Ohm's law 4 times in the total circuit. That's how you got equation number 2. And in individual resistors R1, R2 and R3, that's how you got equation 3, 4 and 5. All this equation you have to put in equation number 1. All right. Then you take an I common and cancel to get this answer. All right. Now let me understand why we need to do it. What I mean is why we need to connect resistors in series. All right. So see, to understand that, you need to know a relation. Current is basically inversely proportional to the resistance. All right. So see, in the formula, you are adding all the resistor value, right? So since you're adding, all right, what you are doing with the total resistance, it's gonna increase. And if total resistance gonna increase, is being inverse proportional, the current will start decreasing. Oh, what is that? It is a method of reducing current. Getting it? So if you are going with some experiment where you need to reduce the current without changing the potential difference, remember, okay, so what you will do, you will add up the resistance like that in series and it will increase and the current start decreasing. So hope you got me today's class really well. That what was it about? It was about why we need to conduct resistors in series. One for hot topic in your class 10 physics, right? So what is a series connection? We did see, all right. After that we have seen that how to get the formula, all right. What is the formula and what are the two specific point about series connection? What gonna happen to current? That was the beginning of our class, right? And what gonna happen to the potential difference? How to derive this formula? Okay, before we derive this, we took an idea by solving this numerical, right? And finally we derived it. That's how we got the answer. We also used Ohm's law concept and that's how we have got the derivation. All right, I hope you got me really well. Okay, I will see you in another episode of physics. Till then, stay healthy.